I imagine a few more people are going to trickle in, but that's okay. Any questions from anyone before we get started? Is the week 2 checkout stuff going okay for folks? I know we saw the Monday group a couple days ago, but everyone feel like that's going along all right?
I have a question about when the lab report is due.
Okay. It's going to be due, the lab report will be due 1 week after the final checkout.
Okay,
So we were just talking about this a little bit. So every 3 weeks is a little bit of a heavier week because you'll have the week 1 checkout of lab 2 and the lab 1 report due in that lab section.
Okay, got it. Thanks.
Yep. Any other questions? I'll encourage folks to, as you're sort of moving large files around among your group members, probably the best way to do that is with Box. I know some people have been emailing things and that works okay, but putting things on Cornell Box on the lab PC is a pretty easy way to move those files around. I'm also I'm gonna make sure it's okay with CIT, but Professor Scovira pointed out that plugging a flash drive into each of the lab PCs might be a nice way to provide shared storage among all group members. So I'm going to experiment with that too. That might be a really nice way for folks to be able to access stuff. The other thing is, with all of your individual, with permission from each of you, I think in addition to, in this class we typically do video recordings of final projects. I think this particular semester I'd like to do, if it's okay with you guys, video recordings of the labs as well, just because this is such an unusual semester that I would kind of like to record how this has worked remotely for the future. So I'll talk to each of you about that, but I just want to sort of give you a heads up that I might ask your permission to do that sort of thing. Okay, so if there are no other questions, I'll get started. You can interrupt me if anything else occurs to you. What I want to do today is continue and finish with the audio demo that we started last time, and then start introducing the equations for Lab 2. Since the Monday groups, they'll start working on Lab 2 on Monday. So we should start looking at these equations in pretty short order. But before I do that, let's finish up this audio demo. I'll remind you what we were doing. So the goal here was to build a bus master that would drive the audio interface on the FPGA to, in this particular example, just use direct digital synthesis to produce sine waves of controllable frequency. So in order to do that on the QSys bus, in addition to the usual system PLL and ARM, we added a few things that we looked at last time. One of the subsystems that we added was the audio subsystem and the AV config, which sets up the audio subsystem. And then we attached the audio subsystem slave input to a bus master that's going to be controlling that subsystem. Then we also added a PIO port to control resetting the state machine and to be able to control the frequency of the sine wave output. So this is what we were looking at last time, and within each of these, we exported a few of these conduits into the Verilog. The AV config, we exported the external interface into Verilog, and you'll recall that we hooked those up to the I2C lines for the FPGA, because this configuration takes place over an I2C link. And then the audio subsystem, we also exported a number of conduits into the Verilog that we hooked up to the audio hardware on the FPGA. And then, of course, we exported the control signals for the bus master so that we could build a bus master state machine to drive that audio system. So in the Verilog, I'll just briefly remind you that these are all the signals that we exported from QSys. So We exported the parallel I/O port that we're using to reset and to set the frequency, and tied that to our own signal in our own Verilog. Exported the AV config signals and hooked those up to the I2C clock and data lines. Exported all of the audio signals and hooked it up to the corresponding audio hardware. And then also exported this bus master, which has really been the subsystem of interest for us for the past little while. That gives us all of the handles that we can grab in order to control this bus. So this is what we were looking at. And then up here, we were working our way through this state machine that would do direct digital synthesis and output it through the DAC. And you'll recall that this DAC is sampling the audio system at 48 kilohertz. So we have to have a sample ready every 48 kilohertz. And because we were sort of running out of time, I figured I'll start at the top with the state machine and go through it, and then run it, and we can see how it works. So our reset state, which in many of the examples on the course website, this reset state is controlled by a push button. Because we don't have access to the push buttons remotely, in this case, we're controlling the reset state via a parallel I/O port. So in this case, if the parallel I/O port assumes a value of 0, that puts the system into a reset state. And when it's in the reset state, it sets the state to 0 for when it ultimately exits this state. Deasserts the read line, deasserts the bus write line, sets a timer to 0, and then also sets this strictly for debugging reset status register to all ones. This is the register that I have tied to the LEDs so that I can visually see when the system is in reset. When this PIO port assumes any value other than 0, it drops out of this reset state and enters state 1, or state 0 rather. In state 0, the first thing that we do is a bus read of the amount of space that is available in the output FIFO. Because you'll recall that we need to, the DAC will look for samples at 48 kilohertz. So at every 48 kilohertz, there needs to be a sample ready. We're generating these samples using the Avalon bus master, which tends to be a little bit bursty. So in order to mediate between something that needs to be very precisely sampled at a constant rate and something that's a little bit bursty, we put a FIFO in between them. So we fill up the FIFO, and then the audio system samples that FIFO at precisely 48 kilohertz. So before we can put a new sample into that FIFO, we need to check if there's any space available in it, and we do that via a bus read. So we set the address that we want to read from to the audio FIFO address, which is defined up here. It's in an offset from 4 from the audio base address, which is at hex 3040. Hex 3040 because in QSYS, we've put the audio system at hex 3040. So that's the base of the audio system. And then add an offset from 4 from that because in the data sheet, in the data sheet, the FIFO space is at an offset of 4 from that base address. So that's why the FIFO address is at hex 3044, offset of 4 from the audio base address. So that's the address that we would like to read from. We assert the bus read signal. We want to read 4 bytes, and then we set the state to 1. We wait for the bus acknowledgement to return. So we wait for the bus ACK to go high. And only once the ACK has gone high do we drop into state 1. In state 1, we set the state to 2. We check the amount of space in the FIFO by shifting the bus read value that we got back by 24. We shift it by 24 because we are interested in these top 8 bits of this FIFO space register. So we shift it by 24, and then we deassert the bus read line. Drop into the next state. If there is space in the FIFO, so if we measure, in this case, more than 2 spaces available in the FIFO, then in that case, we set the state to 3. We do some DDS phase accumulation. We want to write the output of our DDS sign table to the bus. So we set the data that we're going to send over the bus to the output of this sign table. We set the address that we want to write to the audio left address. So audio left address is defined up here at an offset of 8 from the base address, as specified in the data sheet. Offset of 8 from the base address. So we're writing to that particular register. We set the byte enable to, we want to write 4 bytes, and then we assert the write signal. We then wait for the bus ACK to return and then drop into the next state. I'll mention that this state here was in the condition, under the condition that there was space in the FIFO. If there was no space in the FIFO or less than 2 spaces in the FIFO, we sent this state machine all the way back to state 0, and we would try again until space became available in the FIFO. We wait for the ACK, and then we drop into state 4, deasserting the write address. And then we do the same, that was all for the left audio channel. Now we do the same thing for the right audio channel. We set the state to 5. We set the data equal to the same thing that we wrote to the left channel. We set the address equal to the audio write address, which, as we've seen before, this one's offset by C, which if you went to the data sheet, like we've done for a couple of these examples, you would see that that's because it's offset C from the base address. And then we assert the write signal, wait for the ACK, and then go back to 0. It turns out it's important on this system that you write both the left and right channels. You can't write just one. The symptom of only writing the left or right channel is, I believe, silence. Is that correct, Bruce?
Yes.
Okay.
It will not play a sample unless there's valid data for both the left and the right channel.
Okay.
Oh, but just as an aside, the reason that the sign out is shifted by 16 bits there during that assigned to the data bus is that my sign table was a 16-bit signed value for, and the 16-bit signed, and I set the audio interface to be 32-bit data. So unless you want something really quiet, you have to shift it 16 bits.
Okay. Are there questions about this? This is a lot to digest. So,
and this, by the way, where the state where the DDS was done, a couple of states back from this, the state where the DDS is done is going to be the state where you calculate the new drum sample.
so you will be writing your drum sample here. Okay. So let's see what this, yeah.
So you kept on saying that, like, whenever we want to write, you have to assert it by setting the bus write to 1, the binary bit to 1. Can you talk about, like, what exactly actually happens once you do set the bit? Does it then take the bus write data, bus address, and sort of just like figure out what it needs to do by itself?
So if you're asking for sort of the details on how this Avalon bus works, I'm afraid I can't tell you. I don't honestly know. I haven't investigated it that deeply. Maybe Bruce can provide some answer.
So the details of the Avalon bus is some sort of packet network. As again, I mean, this is a really deep rabbit hole. But the control signals are abstracted so that there's a read signal, a write signal, and an acknowledge signal. And the QSys bus that you build will do all of the manipulations necessary to figure out whether you want to read, write, and tell you when the read, write operation is done. And that's all you need to know about it. Yes, there's a lot of automatic behavior which is hidden from you, mercifully.
If you
Right.
want to get like hardcore and do more low-level manipulations of this stuff, you are certainly welcome to. I would maybe encourage you to do something more final project related for that, as opposed to lab assignment related. It's up to you. It's probably will take a lot of time, like final project levels of time.
Okay. Yeah, I was just curious to understand what was going on behind the scenes, but
Sure.
for now I'll just understand to the extent that we do.
Yeah, I know that's a dissatisfying answer, but okay. So let's run this. You'll see that I've joined this Zoom call from the lab PC and pointed the Zoom program to the FPGA board. I'll point out briefly that I'll put together a little tutorial about how to do this. It turns out that in order to have access to the microphone input on the lab PC, you need to do some configuration of your remote desktop connection, specifically in the devices and audio section. So in order to have access to the microphone input for the lab PC, I needed to redirect the microphone here, and I needed to have on the remote PC selected in the play sound drop down here. Again, I'll put this on Canvas so that it's clear, but it's just so you're aware that you might have to do a little bit of configuration, but actually not much at all. So we can run this, and you should hear a tone come over Zoom. So the notion here is that by doing something like this for Lab 2, you should be able to send a command to your board and hear your drum come back into your headphones through your own interface. And like I said last time, my next step here is full loop back so that you can talk to it and have it talk back if you wanted to do some cool voice manipulation stuff. Okay, any questions about this stuff before I move on to some sort of math related things associated with Lab 2? The rest of this lecture and probably most of next lecture is going to be more sort of equations and less QSys and stuff like that. Okay, just interrupt me if anything comes up. So I wanted to, I'll remind you that what the next lab is a physics simulation of the surface of a drum. And we're going to describe the dynamics of the surface of that drum using the 2D wave equation. So a wave equation is a differential equation that relates time derivatives and space derivatives. So it describes a system that's evolving in space and time. And I'll start by writing down the sort of continuous version of this wave equation that we will then discretize into a difference equation that's actually implementable on the FPGA. And I would like to sort of systematically work up to the ultimate equation that you're going to instantiate on the FPGA, because it's not a complicated equation, but it's one with a lot of terms in it. And I think it's an act of cruelty to just drop equations with tons of terms onto folks and then parse through it. I feel like doing that sort of tickles some like fight or flight response part of the brain when you see all this stuff. But if we work up to it systematically, then it looks more like an old friend rather than something that's trying to hurt you. So the equation that we are going to be integrating is this one. It's 1 over c squared times partial squared of u partial t squared oops. You know what? I'm going to do it this way. And cheat. Sorry. I like the pacing that doing the real-time LaTeXing introduces, but this particular week, I'm going to make a lot of mistakes if I try to do that. So the particular equation that we're integrating is shown here. 1 over c squared times the second derivative of u with respect, of u with respect to t. So this is, what we're looking at here is the acceleration of a node on the drum in the perpendicular direction. So we're looking at something like this. Oh my God, sorry. Something like this. So we have some node on the drum that's moving up and down, right? This first term is describing the acceleration of that node in the up-down direction. C here is not the speed of light, it's the speed of sound. So the speed of sound in the membrane. It turns out that when we come up with the difference form of this equation, this abstracts away. But this is 1 over the speed of sound squared times the acceleration of this node in the up-down direction is equal to the 2 second derivatives in the x and y directions. So in this direction, and this direction, and in this direction. This is essentially telling you the difference in stretch between adjacent strings in the xy direction, which is giving you the net force in each direction. And then we have also a dissipative term here, which is describing viscous damping. So we're assuming that this drum is in air, right? And that the air is damping out the movement of the drum. And this you can see is proportional to the first derivative of position here, or velocity, which is what you typically see in damping. Okay. So this is the equation that we're going to discretize. I want to start by just remembering some derivative basics. Stuff that I know you've seen before, but it's probably been a very long time. So we might as well look at it again. So let's recall the definition of a derivative. Which you'll recall from probably high school, goes back to limits, right? So the derivative with respect to time, in this case of some function u of t, is equal to the limit as delta t approaches 0 of that function u at t plus delta t minus u at t over delta t. Do you remember this from so long ago? Right? So as delta t approaches 0, this approaches the derivative of this function u at t. And what we're going to say is that for small delta t, this is approximately equal to this difference equation. Approximately equal to this. Right, so this is for small delta t, this is the the approximation of the derivative. In our equation, though, we have a bunch of second derivatives. So what is the difference approximation of the second derivative? And in order to do this, we're calculating the difference of differences, right? So this looks like the second derivative with respect to t of some function u of t is equal to big fraction of u at t plus delta t minus u at t over delta t minus u at t minus u at t minus delta t over delta t all over delta t. So it's exactly the same form, right? We're just doing the difference of the differences over delta t, which with not tremendously much algebra can be simplified to, whoa, that's huge, of u at t plus delta t minus 2 u at t minus u at t minus delta t over delta t squared. So this is the difference approximation of that second derivative. And you can see that we're going through the process here of discretizing that continuous equation. So I want to, because it's cumbersome to keep track of all these plus delta t's, minus delta t's, I want to introduce a little bit of notation. Which...
Is there a sign error in that? The last minus u t minus u of t minus delta t, shouldn't that be a plus?
Yes, it should. Thank you. So the notation that I want to introduce is shown here. So if we're simulating the surface of a drum, which is a 2D array of a whole bunch of nodes, right, then I want to use the index I to describe the column that this node is in. So the I equals 0 column, I equals 1 column, etc. And the index j to describe the row that it's in. So by subscripting a particular node ij, then we know the particular row and column of the node that we're talking about. And then I want to use the third piece of notation n to describe the particular time step that we're on. So you can see this is the state of the drum at time step n. Some small time step delta t later, we have the state of the drum at time step n plus 1, which just allows us to rewrite the above equation a little bit more concisely. So we can rewrite the above equation a little more concisely. And by the way, I'm introducing this notation because it's in agreement with the paper, which is linked in the reading for Lab 2, that actually derives all these things. So if you look at that paper, the notation that I'm introducing now agrees with the notation in that paper. I think it's equation 2.18 in that paper that we're going to be integrating if folks want to go look at it. So we could rewrite the above equation as d squared dt squared of some u of t is equal to u subscript ij superscript n plus 1, which is to say the ijth node at time step n plus 1 minus 2u ij superscript n, same node at the previous time step, plus u subscript ij superscript n minus 1 at the previous time step, same node, all over delta t squared. So I've rewritten this equation just using some notation that makes things perhaps a little bit easier to look at. So the out-of-plane acceleration of node ij here is given by this expression. Is this clear? Is it boring? Okay, so we can do exactly the same thing for the spatial derivatives. This leads to the following equation, which I had planned to attempt to LaTeX in real time, but given that I screwed up that first much simpler one, I'm just gonna copy and paste it and cheat. But it is based on what we've just done. This should make some sense. So what we're doing here is we are representing our continuous equation in terms of these difference approximations for the first and second derivatives. So we have 1 over c squared times the difference approximation for the time derivative, which we just got from here, right? And then we have two terms here with exactly the same form as the equation that we just came up with, but instead of being in time, they are in space, right? So in this difference approximation, we were looking at the difference between time step n plus 1, time step n, and time step n minus 1. For the spatial derivatives, all those derivatives take place at the same time. So instead of looking at differences in time, we're looking at difference in location on this grid. So for the x derivative, for example, we're looking at node I plus 1j, ij, and I minus 1j. So we're looking at the two adjacent nodes on either side of a node here over whatever that distance is between adjacent nodes. And we'll end up assuming that the distance between nodes in the x and y directions is the same. So delta x and delta y will just be some delta d that is the spacing between these nodes. So precisely the same form, just differences in the spatial dimension along x. This second term, which is the second derivative in y, is again precisely the same form, a difference approximation of the second derivative, but with the differences in the j direction. So now we're looking at the adjacent nodes in the j direction shown here. And then finally, we subtract off the dissipative term, which is eta, our damping constant, times a version of this first expression that we came up with, which is the difference approximation for the first derivative. With the one little piece of subtlety that you'll notice that all of these second derivatives are centered about time step n. So we're looking at time step n and time step n plus 1, and time step n minus 1. So we would like also for our first derivative to be centered around time step n. So we do that by looking at the difference between time steps n plus 1 and n minus 1, symmetrically on either side of time step n. And then instead of dividing by delta t, we divide by 2 times that time step, since they're separated by 2 time steps. Okay, so this equation is the difference approximation of this equation. And assuming that you know initial conditions, then you know all but one term in this equation, right? So if you know the initial conditions at time step, say time steps 1 and 0, right? You'll know the state of the drum at time step n. You'll know the state of the drum at time step n minus 1, right? You'll know the states of all of these nodes at time steps n and n minus 1. So the I plus 1j, ij, all of them, right? You know the whole state of the drum for time steps n and n minus 1. And we will solve for the updated state of the drum at time step n plus 1. So what we're going to do is rearrange this equation to solve for n plus 1, the state of the drum at n plus 1. Okay? Is this okay with people? It's difficult to tell. It's a lot of terms, but we're not doing anything that is individually tremendously complicated. We're doing a difference approximation of each derivative. We came up with just a little bit of notation to describe spatial separation between each node and time separation between time steps. And we rewrote the same equation using difference approximations and using this notation that keeps it a little bit tidier. Okay? So we're going to solve this equation for u at ij at time step n plus 1. But let's first define a parameter. So the parameter that I want to define is, it is a measure of velocity that we'll call rho. So rho is going to be given by c, the speed of sound, times the time step delta t, over the spatial separation delta x or delta y, that we're going to assume they're the same, squared. And we're going to assume that this is less than 0.5 for reasons that I'll explain in a second. Right, so this is a normalized expression for the velocity. It's a normalized speed given in fractions of grid size. Right, so it's a way of describing velocity. And it turns out that this velocity has to be less than 0.5 for the system to be stable. This is called, I think, the Courant condition, I think. So we will make certain, by judicious choice of initial conditions and parameters, we'll make sure that this holds. We'll make sure that this is the case. Otherwise, our drum's going to be unstable. Okay? But with this parameter defined, we can solve the above equation for the updated n plus 1 node. Which, again, I was going to do in real time, but let's not risk it. Let's just do this. And this is the equation that we're going to be implementing. Okay, so this equation here is this equation just solved for u, ij, at n plus 1. And by substituting this parameter wherever this term exists. So we have rho it's here instead of c delta t over delta x squared. So for each node in your drum, you'll be implementing a state machine which performs this operation in order to update that particular node for the next time step. And the challenge in this lab is going to be, like we've already talked about, that audio, the DAC is expecting a sample at 48 kilohertz. So the challenge is, how many of these nodes can you simulate between each 48 kilohertz sample? So you'll build a state machine that does this for a particular node. You'll put lots of copies of that state machine onto the FPGA. You'll essentially fill it up with these state machines, as many as you can. And you'll see how big of a node you can simulate. And you'll have to get the whole node, the whole simulation for the whole drum finished between each time step. And I expect that many of you will be able to simulate nodes of approaching 150 on a side, so up over 22,000 nodes. And we're going to add one more little piece of complication here. One minor, what should I call it? Let's just use terrible vocabulary. One minor thing to improve, to make this simulation more realistic. A nonlinear row. So we are going to make this term rho a function of the amplitude u at ij. The effect of this is going to be that there will be a nonlinear pitch glide. So when you strike a real drum, you will detect with your ear an audible high to low sort of glide in the pitch. It sort of goes pew, right? That's what a drum does. In order to replicate that effect, we're going to have our rho effective equal to the minimum of 0.49 in order to satisfy that Courant condition, and some rho 0, unstretched rho, plus the amplitude in the middle of the drum, so u at ij, plus some constant related to the tension in the drum. So for each node, you're going to look at the nodes all around it. So for node ij, you'll look at I plus 1j, I minus 1j, ij minus 1, ij plus 1 at time step n. And you'll look at the state of that node, the amplitude of that node at time step n, and the state of that node at time step n minus 1. That allows you to incorporate velocity information. And you'll use all of this known information to calculate the updated amplitude of that node at time step n plus 1.
So Hunter, Uij stands for, is basically the amplitude of that node.
Yes.
Okay.
Yeah.
All right.
And you will output to the DAC the amplitude of the middle node in the drum at 48 kilohertz.
Got it.
And there are some opportunities for cleverness here, right? So you look at this, and this is an add, this is an add, a multiplication by 4, so that's a shift, a multiplication by 2, so that's a shift, right? So the only real multiplies that we have in this expression are this multiplied by the reciprocal term, this multiply, and a multiply by rho. With careful selection of eta, we're not telling you what eta needs to be. You can pick eta yourself. You could make this a power of 2 and turn this multiply into a shift as well, and this one into a shift as well. You will have to do a no-kidding multiply by rho, right? But these sorts of optimizations are going to become important, because if not today, then next time I'll show you in the compilation reports in Cordis. So when you compile a project, it develops a compilation report, which we haven't really looked at yet in this class, but it tells you all of the hardware that you're using on the board. So it tells you you're using, 10 of 174 multipliers. You're using this % of memory. And in this lab, you are going to be building a system that gets right up to the limit of what you can fit on this board. So you'll be, for example, trying to exhaust every multiplier that you can exhaust in order to fit more drums on here. The constraining resource here may be different for different groups. Some of you may run out of multipliers, and that might be the reason why you can't build a bigger drum. Some of you might run out of memory. In lab 1, the state for our system was very simple. It was just 3 states. The sort of the X, Y, and Z states was all that you needed to store in order to update to the next state. In this case, the state for your system is the state of every node on your drum. It's going to take up quite a bit of memory. So the next topic that we're going to cover in lecture is memory on the FPGA, how to build it and how to manipulate it, because that's going to be really important for lab 2. But some clever optimizations here allow for you to push the limit and add more and more nodes to this FPGA. And there are some things that you're going to have to be careful about that I'll talk about. I guess I'll talk about it next time. You'll have to be very careful about overflows here. You'll have to be careful about initial conditions. With regard to initial conditions, you have a few sort of options. If this is your drum here, one option for initial conditions is to build some sort of a linear pyramid on the drum. So to assume that initially you're sort of holding the drum in this configuration, and then you let go at time step 0 and it oscillates. To the extent that you can help it, it's good to avoid discontinuities. This does have a few discontinuities. It has a sharp point. It has some discontinuities here, but it doesn't introduce too many problems. The drum sounds pretty good with these sorts of initial conditions. If you wanted to be a little more ambitious, you could maybe do something Gaussian. You could set up your drum to initially be in this configuration and then drop it. This has less discontinuities, but setting this up requires a little bit more work than the linear option rather. A third option I would say is you could do some sort of exponential initial condition. The initial condition to avoid is an impulse. You can't just hold one node high and have all the adjacent nodes low and then let go. Because if you do that, you're going to get aliasing. Weird things are going to happen. So you can't do an impulsive initial condition. You want something continuous.
If I can expand on that slightly, you have to avoid aliasing in time, as you all are familiar with. But this system can alias in space as well as time. And so you have to make sure that your initial condition does not violate aliasing in space specifically.
So next time I'm going to start with the equation that we ended with today and talk a little more carefully through some of the opportunities for optimization that exist in that equation. And then in subsequent lectures, we'll talk about strategies for implementing that in hardware on the FPGA and for parallelizing it. Okay, any questions? Okay, then in that case, I'll see some of you this afternoon and I'll see the rest of you on Friday.